Warning: nitric acid and sulfuric acid are highly corrosive. Wear gloves when handling them. Distillation of nitric acid produces nitrogen dioxide fumes. This experiment should be performed outside in a fume hood. Fuming nitric acid is dangerously reactive with nitrile gloves. Vinyl or other fluoropolymer gloves are recommended. Greetings, fellow nerds. For the past couple of months, we've been making nitric acid, and at this point we'll have accumulated lots of nitric acid from various runs at various concentrations. But having a single or a few standard concentrations is much more practical, as most literature procedures are written starting with those standards. The most common standard concentration is azeotropic nitric acid at about 68% to 70% acid by mass. There is also a form called fuming nitric acid that's usually pure 100% nitric acid or close to it. It's called this way because it fumes. Aside from being simply more concentrated, fuming nitric acid has different reactivity than the more common azeotropic nitric acid and can even be viewed as a separate reagent and not interchangeable with it. So it's worth having alongside azeotropic nitric acid. However, it cannot be made by fractional distillation of concentrations less than azeotropic acid, because once we reach the azeotrope, we cannot go further without special procedures. Now I know I promised years ago not to do another fractional distillation video because once you've seen one, you've seen them all. But this time is a little different because I'm going to be using a drying agent to get past the azeotrope that normally prevents us from retrieving higher concentrations from lower concentrations. First, we need to make azeotropic nitric acid. I have here diluted nitric acid that I made previously from various wet process and dry process techniques, and used various nitrate salts as well as sodium bisulfate. The concentrations range from 10% to 65%. In a very large flask, we combine them all so we can distill everything at once. At this point, some amateurs might add some additives like hydrogen peroxide to react away any lingering nitrogen dioxide, but I find the yield improvement to be negligible. Once everything is mixed together, we install on top Vigro fractional distillation columns totaling about 1 meter or 3 feet in height. I didn't have a column that big, so I just used 2 smaller ones. Because of the very large size of this setup, I can't film the whole thing at once, and it actually doesn't fit in my fume hood entirely. So I'm going to set it on the floor just outside the fume hood. As usual, we insulate the flasks and columns with aluminum foil, and on top of the columns we install the traditional condensers and adapters. Now we turn on the heating and begin fractional distillation. I find nitric acid to be a little more difficult to fractionally distill than other mixtures because it seems it doesn't fractionate that easily into water in the azeotrope, especially if you use high heat and overdrive the columns. Rather than getting water first and quickly transitioning to the azeotrope, you get very dilute nitric acid that boils slightly above the boiling point of water, and then the temperature rises slowly but wastes a lot of distillate before reaching the azeotrope. Sometimes it doesn't even reach the azeotrope at all. The problem is that nitric acid requires much more time in the columns to separate than other solvents. So if you use high heat, the columns get flooded with vapor and do not fractionate very well. The solution is easy, but you do need to be aware of it. First is to use as long a column as you can to give better separation, which is why I'm using 2 Vigro columns. Second, and most important, is to use less heat and instead distill slowly and gently instead of brute forcing with high heat. It's helpful to focus on the rate of distillation rather than the temperature. Adjust the heating until the rate is slow enough to get the appropriate temperature. So if you see the temperature not being stable but still distilling, then adjust heating downward to slow down the rate. If nothing is distilling, adjust upward again. I had to adjust to get 1 drop of distillate every 10 seconds before my distillation was stable. You can see now I'm getting the right temperature of boiling water, and it's maintaining that temperature rather than flooding and ramping. The drawback, like with most fractional distillations, is that this is very slow. I had to distill for several hours. So it's helpful to start with nitric acid that has as little water as possible. This is why I encourage the use of dry processes for making nitric acid. The less water you add, the less water you need to remove later. Anyway, as the distillation progresses, the temperature will begin to rise despite the rate of drops remaining constant. We're now entering the transition phase of the fractional distillation. The receivers changed out and the distillate up until that point is mostly water with negligible amounts of acid. So you can discard that if you want. Now we collect the middle fraction, which we keep. You might even need to raise the heating to maintain a constant drip rate in the condenser, although I didn't have to. Eventually the temperature will stop rising and we're now collecting azeotropic nitric acid. At this point I actually recommend turning off the distillation and stopping. This is because we've already distilled off all the lower fractions. The last fraction has to be azeotropic nitric acid. Thus, there is no need for further fractional distillation or even distillation. So you can save considerable time by just using the nitric acid in the boiling flask directly. But if you still want to purify it in case there might be non-volatile impurities, you can do so by letting it cool first and then reassembling the apparatus into a simple distillation apparatus along with changing out the receiver. Then performing simple distillation of the acid we know is entirely azeotropic nitric acid. No need to waste time continuing the inherently slow fractional distillation. Anyway, there is our product azeotropic nitric acid. It's a bit yellow due to slight decomposition of nitric acid producing small amounts of nitrogen dioxide. It's negligible, but if you want to remove it, a simple way is to boil it off by distilling off a small amount of acid and stopping. The nitrogen dioxide will get boiled off and you'll clarify the acid. And here is our three fractions: the first fraction, the middle or transition fraction, and the final or azeotropic fraction. I measured their densities and checked that against a table of known concentrations. As you can see, the first fraction is water with negligible acid. We can discard this. The middle fraction has a concentration of about 41%. We can save it as dilute acid and feed it forward into future runs. Alternatively, since we have to remove the water anyway, we can make it useful by adding it to dry process nitric acid runs and improve the yield a bit by making them wet process, but without adding in extra water. Anyway, at the end here we have our azeotropic nitric acid. I measured the concentration to be 65%, or a bit lower than the 68% of standard azeotropic nitric acid. But this is close enough for amateur work and within the error of my measurements. I recommend storing this for later use as azeotropic nitric acid or diluting it to the appropriate concentrations whenever you need nitric acid. And that's how you fractionally distill dilute nitric acid to obtain azeotropic nitric acid. But of course, if that's all I had to say, I wouldn't make a separate video. The true topic of this video is getting fuming nitric acid. Of course, the best and most straightforward way to get fuming nitric acid is to make it directly by reacting sulfuric acid with a nitrate salt, like sodium nitrate, and distilling off the fuming nitric acid. Because there is no water present initially and none is created during the process, the nitric acid will be inherently water-free. I strongly recommend this method for its simplicity and speed. However, you may be producing nitric acid from wet sources or using different reagents that already have water in them. For example, making nitric acid from sodium bisulfate tends to produce lower concentrations because sodium bisulfate tends to already have water in it. In that case, after we fractionally distill to produce azeotropic acid, we need an upgrade process to produce fuming nitric acid. As said before, fuming nitric acid cannot be reached from just distilling diluted nitric acid, because once you reach the azeotrope you can't concentrate any further. The distillate will always be the same azeotrope concentration. The usual approach to break an azeotrope is to add a volatile substance that forms another azeotrope at an even lower temperature and remove one of the components that way. We did this before with toluene and water in my previous video on the D-Stark apparatus. However, nitric acid is very reactive, and adding an organic substance to it is generally not a good idea, since you tend to make explosives. Fortunately, there is an alternative approach where we add a substance that reacts with or absorbs one of the components more strongly than the other. Then we can fractionally distill off the other component. We've actually done this a lot before using molecular sieves. However, molecular sieves are destroyed by acid, so we need to use something else. The two most common substances in the industry for nitric acid upgrading are magnesium nitrate and sulfuric acid. They can both be regenerated after use and recycled, so you won't deplete them if they're valuable to you. For this reason, some amateurs prefer to make nitric acid using low concentration producing processes and instead upgrade their nitric acid using sulfuric acid, which can then be recycled. While using up the sulfuric acid to make fuming nitric acid directly is faster and more convenient, some amateurs may not want to waste it. If sulfuric acid is completely and totally unavailable, then magnesium nitrate may be used. It might sound exotic, but it may be available as a fertilizer to you. Alternatively, it can be made from nitric acid and magnesium carbonate. Unfortunately, I couldn't find a cheap and trustworthy source of magnesium carbonate, so I decided to make it from two additional very easy to obtain chemicals, magnesium sulfate and sodium carbonate. First, we get 500 grams of magnesium sulfate heptahydrate and stir it with 500 milliliters of water until dissolved. Magnesium sulfate is easily available from grocery stores and pharmacies as Epsom salts. In a separate container, we get 250 grams of sodium carbonate and stir in 750 milliliters of water until dissolved. Sodium carbonate is available as washing soda and as a pH-raising chemical for swimming pools. If you're really having a hard time finding it, you can also heat to decompose sodium bicarbonate or baking soda until the mass no longer decreases. Anyway, we mix the solution with the magnesium sulfate solution from earlier to make a precipitate of magnesium carbonate. We then suction filter the magnesium carbonate. Anyway, if you can buy directly and cheaply, then you might want to go that route instead. For me, it was actually faster and cheaper to make it. The chemicals were basically just across the street from me. Okay, moving on, we just reacted with excess dilute nitric acid until completely dissolved. You can even use that transition or middle phase acid we had earlier. I know it seems a bit wasteful to use nitric acid just to make a desiccating reagent, but we're making lots of nitric acid anyway, and once the magnesium nitrate is made, it's recyclable and thus you only need to make it once. Okay, we now have our solution of magnesium nitrate. It doesn't normally fizz like this. This is happening because I just finished reacting it with the nitric acid and the carbon dioxide is still being released. Anyway, we dried the magnesium nitrate by distilling off all the water. Magnesium nitrate actually decomposes before it completely dries and solidifies, so you'll need to be careful or keep the temperature below the decomposition temperature of 330 Celsius. I set my hot plate to about 320 Celsius and kept heating until the water stopped distilling over. Then I turned off the heating and let it cool. At this point I want to mention a special note about molten salts in Erlenmeyer flasks. If you let them solidify on the bottom like this, you run the slight risk of shattering the flask when you reheat and melt them later. This is because the very bottom will melt and expand, but the top of the mass is still solid and holds the molten salt down. Normally the danger isn't that high because the top would have contracted during cooling and allowed the salt to ooze out the sides. But to reduce the risk further, I like to tilt my molten salt flask like this. It'll solidify like that, and when I reheat and melt them later, the molten salt can easily ooze out the empty side. At this point, having watched my videos before, you might be asking if you can react magnesium sulfate with calcium nitrate to produce magnesium nitrate, an insoluble calcium sulfate that can be filtered. You can, and it works, and I tried it, but I found it to be incredibly labor intensive because the calcium sulfate is hard to filter, and I can't use suction filtration for fear of clogging up my filter frits. The mixtures were also pretty thick and hard to pour, and I had to use bucket-sized quantities of water to make it thin enough to work with. After 2 weeks of working on it, I totally abandoned that pathway and just decided to use the magnesium carbonate pathway instead. It's quicker, easier to work with, and the allowance of suction filtering means this can be done in a day rather than 2 weeks. Anyway, we're done and ready to use the magnesium nitrate for upgrading azeotropic nitric acid. Before we do that, I must mention that when distilling fuming nitric acid, a major problem for the amateur is that ground glass joints tend to seize up. The fuming nitric acid is so reactive that it breaks down the silicone grease normally used to grease such joints. As said before, fuming nitric acid can be viewed as a separate reagent all itself with separate dangers and considerations. To prevent this, professional chemists use PTFE or Teflon sleeves in the joints since these are not degraded by the acid. Unfortunately, they are ludicrously expensive for the amateur. A cheaper, although more cumbersome approach is to wrap your ground glass joints in 1 or 2 layers of PTFE pipe thread tape, which is used for plumbing. You'll have to be careful not to grind off the tape when inserting the joints, and you'll have to replace the tape when you disconnect them. It's also prone to leaking, so you'll need to recheck your work as you run and fix the leaks before continuing. But at least your joints won't seize up and will be much easier to disconnect when you're done. Some amateurs also like to use concentrated sulfuric acid itself as a lubricant. I've tried that myself and it does work, but I found it to be unreliable and still got the occasional locked joint. so I prefer to use PTFE pipe thread tape. Okay, so let's start using our magnesium nitrate. I have here about 300 grams of magnesium nitrate, so I decide to arbitrarily add in 300 milliliters of concentrated azeotropic nitric acid. I'm not sure if this is the optimal mixing ratio, but we'll find out soon enough. As usual, we set up a fractional distillation setup and start distilling. Once again, temperature and flow control need to be gentle. To maintain stability, I had to adjust the heating to maintain a flow rate of about 1 drop every 10 seconds. It was very slow, but if I tried to go faster, the temperature would start jumping much too high. Pure fuming nitric acid has a boiling point of about 83 degrees Celsius. I'm somewhat below that here because some of it is decomposing as it goes up to columns, and because my digital thermometer is somewhat inaccurate. Especially with such a low flow rate, it might not be equilibrating enough to get an accurate reading anyway. Oh, before I forget, I want to draw your attention to the fact that I'm wearing vinyl gloves while changing the receiver. Fuming nitric acid sets nitrile gloves on fire, so you shouldn't wear them while handling it. But vinyl gloves offer better protection toward fuming nitric acid. I tend not to wear it because nitrile is better for most other cases, but in this case vinyl has to be used. Okay, it took about 8 hours, but I eventually got around 70 milliliters of purified fuming nitric acid, before the temperature quickly started rising to the boiling point of azeotropic nitric acid at about 120 Celsius. We then let the apparatus cool and then reassemble it into a simple distillation apparatus. The magnesium nitrate is obviously saturated with water at this point, so we regenerate it by distilling off all the water and leftover nitric acid. Treat it like you're drying it. This time we save the distillate because it's basically weak nitric acid that we can fractionally distill again. As before, I carefully tilt the flask for cooling so it doesn't shatter when I reuse it and remelt the magnesium nitrate in the future. If you want to store the magnesium nitrate separately, you may need to dissolve it in water to get it out of the flask. So that's using magnesium nitrate for drying azeotropic nitric acid to produce fuming nitric acid. It seems to be reasonably effective and can easily be made from readily available chemicals if you cannot obtain sulfuric acid. But if you can get sulfuric acid, then that's the drying agent of choice for the amateur. I'm going to test it out starting with low-grade drain cleaner acid. As usual, the drying agent itself must first have water removed by heating it. My hot plate is not hot enough to boil the acid, but I don't need to. I just need to distill off as much water as I can to get the most capacity. We can always use more sulfuric acid if needed. The contaminants in the acid that give the color will decompose during this process, so you'll see it get lighter as time progresses. When no more water seems to distill over, let the acid cool back down to room temperature. Do not attempt to handle boiling hot sulfuric acid. It will not end well for you. It tends to instantly dissolve flesh. To 300 milliliters of azeotropic nitric acid, we add 300 milliliters of our recently dried concentrate sulfuric acid. Add the sulfuric acid to the nitric acid with stirring. The temperature will rise, and if it gets hot enough to start boiling, stop and let it cool before continuing. Once again, we connect up our fractional distillation columns and distill off the fuming nitric acid. Performance seems to be a lot better this time, and it didn't feel like I needed to be as touchy with the temperature controls to get a good flow rate at constant temperature. I was also able to run a little faster than magnesium nitrate. I got around 150 milliliters of fuming nitric acid before the temperature starts spiking. Once again, the heating is then turned off and allowed to cool before reassembling it into simple distillation apparatus. The sulfuric acid is regenerated by distilling off the very dilute nitric acid. It seems that the nitric acid also destroyed a lot of the impurities in the sulfuric acid and made it very light in color. Anyway, there we go. Fuming nitric acid and the depleted dilute nitric acid behind them made using two different drying agents, magnesium nitrate and sulfuric acid. The depleted acid in both runs still had significant nitric acid left over, so I think I saturated the drying agents. This allows us to compare their performance. However, because I use different amounts of drying agent in each run, to better compare them, I'm dividing the mass of the nitric acid produced from the mass of the drying agent used. They both seem to give very similar performance on a mass basis as long as you add excess nitric acid. The variability in my own technique is probably a bigger contributing factor. So if performance is similar, we should look to cost and labor to see which one is better. Initially, sulfuric acid is the cheaper drying agent because you don't need to waste a lot of reagents making the nitric acid needed to make magnesium nitrate. But since both drying agents are regenerated and recycled at the end of each run, the cost becomes a non-factor over time. In terms of labor though, I think sulfuric acid is the better drying agent. It's easier to work with being liquid rather than a solid, and it seems to be easier to distill from with less temperature control sensitivity than magnesium nitrate. So I recommend using sulfuric acid first if you have it, and do not wish to use it up making fuming nitric acid by direct reaction with nitrates. And if you don't have access to sulfuric acid at all, then magnesium nitrate may be made if you can spare the initial labor issues. Okay, so that's how we make fuming nitric acid using a drying agent. You might be wondering if you can clarify the acid from the nitrogen dioxide by using our old trick of distilling off a little. I tried that, and while I'm sure we reduced the nitrogen dioxide content, visually it wasn't very impressive. And for the amateur, there isn't much point. Almost all reactions that can be done with white fuming nitric acid can also be done with not so white fuming nitric acid. But if you really want to get it clear, you can perform vacuum distillation. Alternatively, you can add a small amount of urea or ammonium nitrate to destroy the nitrogen dioxide, but you also generate water and reduce the purity of the acid. I didn't bother with either. So that's how we use fractional distillation to purify dilute nitric acid into concentrate azeotropic nitric acid, and then use a drying agent to break the azeotrope and produce pure fuming nitric acid. So the obvious question now, what do you use them for? Concentrated nitric acid is an oxidizing acid, so it's good for dissolving metals like copper that other acids cannot dissolve. Meanwhile, fuming nitric acid is highly reactive and used extensively for nitration reactions. Being a very powerful oxidizer, it's also used a lot as a component of hypergolic rocket fuel. I actually want to try a bit of rocket fuel chemistry and maybe some organic nitration chemistry. I also just need azeotropic nitric acid in general to replenish my supplies. Anyway, I hope that video is interesting to you. Thanks for watching. Special thank you to all of my supporters on Patreon for making these science videos possible with their donations and their direction. If you're not currently a patron but would like to support the continued production of science videos like this one, then check out my Patreon page here or in the video description. I really appreciate any and all support.